So today I'll revisit the LQR because it's such an important tool. And then I'll give further examples of design. And then I'll give more examples of more complex control systems like for path following. And I'll present the challenge that I would like to be involved in that. So I'll share it with you. And then, so maybe we don't have more time or much time to cover more than that today. And tomorrow we probably have to go for an extra session. Well, we should go for an extra session because I still have to cover a little bit of navigation and cooperative motion control. All right. So remember what I told you. So this is a brief overview of the torque that you apply, and you have the omega, right? Or the theta. And then torque is equal to moment of inertia. Let's assume it's equal to 1, d2 theta, dt2. So suppose this thing is rotating, and you want to steer the theta from some initial position to some desired position. So take theta to theta reference asymptotically. And this was a very interesting example and so simple to illustrate the key ideas behind the LQR. So I thought I would go very briefly over this again because it's important. So the first thing you have to remember is that when we study LQR, the system itself is no longer described in terms of one single differential equation of order 2, 3, 4, or 5, but my many differential equations of order 1. And when you stick them up, then when you look at the thing, wow, this looks like a single first order differential equation, which is not because it involves vectors, but it's a way of standardizing things and making things more efficient, because no matter what the complexity of the system is, then you have a uniform way of representing it. And remember that trick I mentioned to you. So what you do is the following. First, you look at the physics of the problem. And you know that if you have a second order system, and if you open your eyes at some point and apply a torque and wish to find out what the future will be at that particular point, you should have information about theta and theta dot, two variables. So this is called the state. So T and theta dot. So it's a necessary and sufficient condition to predict what is happening in the future when you start at some arbitrary instant of time. So it's the state. It condenses all that you know about the system in a deterministic system, of course. And then remember, I told you the following. In control theory, when you write the equations, we deal with the vectors that are called X. So X, that I'm going to call X1 and X2. And I could assign theta to X1 and theta dot to X2. It could be the other way around. It doesn't matter. It doesn't matter really. Okay. So again, instead of a differential equation of order 2, and you write the equations for this, and I'm going to be quick here, you get the derivative of X is equal to X1 dot X2 dot equal to theta dot, but theta is X1 and theta dot is X2. Okay, now you still have equal to, yeah, plus, and now you input this here, 1, 0, and the torque. In fact, the second derivative is 0. No, not the second derivative is 0. The second derivative, which is the angular acceleration, is the input torque. These are the equations. And now you can write it in this form, x dot equal to a x, where x is a vector, plus bu. So input sometimes we call u, so t. This is a matrix, this is a matrix. So this is, I'm doing many stupid mistake, right? This is x2. Plus 0, 1, t. So derivative of x1, which is the derivative of theta, is equal to derivative of theta. So you pick up the x2. And then the derivative of theta dot is equal to the input. So you get 0, 1. So you get A, and this is B. And this is what you see when you formulate control problems in formulation in state space, because it gives you a uniform language setup. All right. Then I told you the following. So suppose you start by declaring the following. I want to drive position and derivative to 0. So it's spinning. You start at some position and then you want to drive to 0. So what I told you is that a very naive approach would be, well, you pick up x1, you pick up x2, multiply by again, multiply by again. It's the simplest kind of control law that you can come up with. So you do feedback from the position theta and from the rate of theta. Now, the interesting thing, as I mentioned to you, you can always write this as u equal to k1, k2, x1, x2 minus, and this is now matrix A, K, and this is X. So again, in a very abstract setting, the feedback is a scalar. This is a scalar. This is a vector. And of course, this is a matrix 1 times 2, 1 times 2. When you close the loop, then you get x dot equal to ax plus bu, u equal to minus kx. So you get x dot equal to a minus bk x. So now what do you wish to do? You wish to choose k such that this system will be stable. In other words, all the trajectories will go down to 0. But this is not enough, because you want to do more than that. I mean, you want to analyze the trade-off between speed of convergence to 0 in the energy that you spend. And this is what I mentioned to you. You do the following. Okay, let me make this formal. When I start at x bold 0, and I drive this with, for example, at the origin, it doesn't matter. This is the torque. Then you get something theta of t. And then, of course, on another graphic, theta dot of t, all right? So ideally, you'd like these guys to come down to 0 relatively fast. So this means that if you square the area under each one of them, you want this area to be very small. That's what you mean by a fast system. So what you want to do is to penalize or optimize by proper choice of u the integral between 0 and infinity of x1 square plus x2 square. That's what you have here. So this is, if this number is large, it means that for very long periods of time you are away from the origin and the system is not doing the job of being driven to the origin. On the other hand, when you look at the expression minus k1 x1 minus k2 x2, okay, if you play with these gains, And I'm going to give the intuition later. When you increase these gains, you make this squeeze down to zero faster. But then you get the U that may be very large, and you may saturate even your actuators. So then you put a term there where you say, well, wait a moment, because I don't want to spend too much energy. And this is how we are measuring the energy in this case. So this is the simplest case, as I mentioned to you, of the famous LQR problem. So it's a linear system. It's a quadratic cost. This sometimes it's called the cost. And regulated because you want to regulate to zero. Okay. So what I told you then was the following. You now have to find a way of, given X naught, compute the gains K1 and K2 such that when you apply this control law, everything gets down to zero. So there are many ways of doing this. For example, in this specific case, if K1 and K2 are positive, they will do the job. But as I mentioned to you, it's a bad choice to penalize simply x1 squared plus x2 squared. Because if you are thinking of more complicated problems where one of the variables, as I mentioned to you, has to do with distance and the other one with orientation, maybe milliradians, if you penalize them equally, the milliradians will go out the window. You don't even see them. So you have to bring things up to the same level. And that's why I introduced the weights that I mentioned to you. You look at the function k1x1 plus k2x2. And this is where your engineering judgment comes into play. So for example, if this is in meters, and if this is in milliradians per second, okay? You put, and if you want to say, for me, it's equally bad to have large errors on the order of meters or errors on the order of milliradians per second. Then you have to increase these gains so that they come up to the same level and can be compared. This is crucial in the design. That's where your engineering judgment comes into play. And I told you that what you do is to an artificial signal, which is k1x1 plus k2x2, that I'm going to call Cx, where C is equal to Q1 and Q2, all right? And then I rewrote this as minimize by proper choice of U, the integral between 0 and infinity x transpose qxy, because when you do, for example, k1x1 square, sorry, what you get here is x1 up, x1, x2, k1, k2, and you get x1, x2, and this you call q, positive definite. So that's what you have here. So sometimes in the books or in the literature, you see the problem immediately formulated in this manner, and you start, where does this freaking k come from? So one way of interpreting this is exactly what I told you, okay? And then you put the rho u square dt, all right? So now you have a way. I showed you there's a trade-off when you find the optimal solution, and the trade-off is as follows. If you put here the energy of U, and here the energy of the state, it does something like this. So if you want this guy very small, in other words, go very quickly to the origin, you have to pump up the energy that you give to the system. If you are not willing to give the system a lot of energy, then you have to accept that the errors will be large. That's the proper trade-off. Now, the beautiful thing is when you have x dot equal to, ax plus bu, and j integral x transpose qx plus rho u squared dt. the following question arises. Does there exist a control law? Hopefully using state feedback that will minimize this and make the system stable. And what Kalman has shown is that under very general conditions, yes, this is true. And when you go to MATLAB and solve the LQR problem, you can key in the A, the B, the Q, and the rho. And MATLAB will spit out the control that does the job. That happens to be state feedback. You see, if you gave this to an engineer, or sorry, to a mathematician other than Kalman, he or she would probably try to solve this problem for each x naught. I start at x naught, the initial state, and I solve this problem. And maybe he or she would find a contrived way of coming up with an input that would minimize this. And then he would store this input in the computer and apply in open loop, and that's it. But this will never work because you have to avoid open loop strategies, because otherwise you are going to be very, very sensitive to small perturbations in the parameters. So the beauty about Kalman's result is that whatever comes out of this is in the form of a state feedback. So you have feedback from position, theta, and you have feedback from rate of rotation, which is a beautiful result. Okay, it's a very deep result. Okay, then I gave you some examples here. Okay. So now let's learn how to do this. So suppose, okay. So you see, you have this. Now you have U, which is the torque. Then you have theta dot, which is x2. And then when you integrate, you have theta, which is x1. And what Kalman tells you, if you want to derive these states to zero with proper balance between the energy you spend and the performance of the system, all you have to do is to compute the gains. And here you have K2, and you feed in there. Here you feed in there. And you are done. Okay. Now you may comment, well, come on, this is trivial. It's true. But when you have a very complex system like large space structures and stuff like that with hundreds of variables, if you can get your hands on the variables that jingle inside, then I'm exaggerating a bit. It's not necessarily like this, but essentially what you end up doing would be to have state feedback from all the variables, and that's it. There's no other complexity introduced. I also mentioned to you that, okay, this drives to zero. How do I make theta follow a certain reference? Well, you stick the reference here, theta ref, and then you put, oh no, this is bad. And then you put the K1 here. And then so from a stability standpoint, you have not changed anything, because what you see here is minus K2 times X1 minus K1 times X2 minus K1 times X1. Okay, you introduced this, but stability of a linear system does not depend on the inputs. So you are done. You are basically done. All right. So now let's study this. This is a second order system. Another important thing that you should do when you design a complex control system is, this is my opinion, to do the design using state space methods and then the analysis in the frequency domain, using the Bode diagrams. Because there you have a lot of intuition as to what's going on. If you write in closed loop what is the differential equation that this obeys, it's x1 plus k2 x1 plus k1 x1 is equal to k2 well, x1 reference. So it's a nice second order system. And you already know, that, which is obvious, that this guy here, because it's multiplying a derivative, it's playing the role of a damping effect. And this one is playing the role of a spring effect, that one. All right. So now, when you look at the second order system, I'm assuming you know that you can write this in canonical form, plus 2 psi omega n psi 1 dot plus k1 omega n square is equal to k1 x1 rev. So this is the natural frequency of the undamped oscillations, and this will give you the damping factor. So now suppose you do a design, and now you do the following. Okay, let me see if it works. So you input a reference, x1 reference. The output will go to exactly x1 rev because it's stable, it will reach steady state. This means this goes to 0, so x goes to x1 rev. But suppose you get something like this. Oops. Too many oscillations. Okay. Now, again, in this case, it's trivial what one should do, but you learn with these very simple cases what to do in the more complicated cases. When you look at this, what is your first comment? X1 is not sufficiently damped. So X1 has a lot of oscillations. If X1 has a lot of oscillations, X2, which is X1 dot, oscillates even more. Even more. So I'm going to exaggerate. I mean, it could something like that. So now, if you go to the criterion, which is J equal to the integral between 0 and infinity, K1 x1 square, which is theta, plus K2 x2 square, which is theta dot, plus rho u square dt. When you see this, when you see this, what should you do? It's obvious. You look at this and say, oh my God, the derivative does wild oscillations. So when I compute the integral of the derivative times this coefficient, I should be able to penalize it very much so that the oscillation gets squeezed down. And the strategy is to increase K2. See, that's how you do the design. You have to look at the solution, and if you have too many oscillations, the system is not sufficiently damped. This means that the derivative is taking large excursions. Therefore, when you compute the integral of this, you get a large number. Well, put a large penalty there. I'm going to exaggerate 1,000. If you have 1,000, and if you have large excursions, this is huge. And the system, the solution will try to bring it down by choosing other K1s and K2s. And in fact, what it will do, in the end, it's going to increase this number here, and therefore it's going to increase the damping factor. So this intuitive behavior is very, 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 very important. So that's the transient behavior. Now let's look at something else. Oops. Okay, I don't know if you know this stuff, but when you have a system from x1 ref to x1, described by this differential equation that you have here. And if you excite the reference with sinusoids with the same amplitude and augmenting frequency, so you have this. Usually you do this on a log-log plot. This is what we call Bode diagrams. I don't know if they have other names. Bode? Bode plot. So you see, what you see here is the following. This is 0. When the frequency has, when the input wave has a very small frequency, and you excite and watch the output, basically the output at the same frequency is essentially the same. It's also 1. And then as you increase the frequency, this thing starts coming down. Well, it's not exactly like this, but sorry, this is not correct. There's a famous point here that is called, omega n. And then you may have responses like this, or like this, or like this. And this point is closer and closer to this point here. This is when C goes down. So again, if you look in the frequency domain or using Bode plots, if you study the response of the system in time or in frequency, and if you see these large peaks, you go and increase K2 and it will squeeze them down. And now comes a very, very important point. Suppose you get a relatively nice system. Remember, we are trying to control something very easy, right? It's something tumbling in space and you want to drive from one angular position to another one asymptotically, and then at that point, asymptotically, the derivative will go to 0. Suppose you could achieve a design where you get something very smooth, omega n. Maybe a little bit of overshoot, and then you have this thing. The question is this number okay? So the damping, we already took care of this, right? We already took care of that. So what happens with the omega n? What should omega n be? It depends on your application. Remember that there is an intuitive explanation to this. I mean, you hear, at least in electrical engineering, you talk about the closed loop bandwidth of the system. And I mentioned this to you. I mean, if you have that wall over there, let's assume it's linear, and you excite with frequencies, with amplitude 1. So if you plot this, let's say you get something of this kind. So this means that if you excite the system with harmonics roughly up to here, and all the energy is concentrated here, you can hear very well what's going on the other side. If you have a philharmonica that has very, frequencies that are very high, when you excite the wall with these signals, then you get some very large attenuation, and it won't hear very well. And that's why you look at the bandwidth of your speakers. It should be up to whatever the maximum frequency of the human being can hear. So how do we specify the omega n? The person that requests the design is going to tell you, I want a certain bandwidth based on the physics of the system. So suppose you could control the psi, and now you reach the conclusion that this is very small. For example, 0.001 radians per second. And you really would like to bump it up to 0.05 radians per second. What do you do? So what you do is you tell the system not to be greedy, because energy is cheap, and you decrease the rho. When you decrease the rho, you see this stretching. Okay. So remember, this is a very simple case where you are controlling the damping by penalizing the derivative, and you are increasing the bandwidth by decreasing the penalty on energy. Energy is cheap, so you can do whatever you wish, and there's no big deal. Okay. All right. So now that we know this, let's go for the non-bottom model number one. I don't know if there are any questions at this point. These principles are very simple, but behind the principles, a very deep theory. Okay. So the non-bottom model is R dot equal to minus AR plus VU. So you have the rudder, it's going at a certain speed, I don't care. You have the rudder, and at about a nominal speed, then when you move the rudder, then you get the R moving. Okay. We already know from the first part of the course that if you end up with a control law, that is this, just a K and then a reference, you have a problem, or you could have the K out there. You are going to have a problem because you don't get the steady state error equal to 0. Why? Remember what I told you, when you walk across the top path, you don't see any integrator that is isolated. So this is not going to work. And this means that there's a problem. Hmm? Thank you. Here. Thank you. So as we know, the recipe is to have an integrator there. So I taught you the very simple thing that you should have an integral action. Then you have something you call K1. And then you have the non-bottom model. Number 1, this is R. And you have this thing. And then you could have the error. And this is the reference. Okay, but how can we obtain this? Because when you have the non-bottom model, you only have one state. So if you go through Kalman and do the design, you get one gain. And this is not good. So what we do is a simple trick, which is the following. Remember what I told you with nonlinear systems, when you look at the system and it looks ugly and you want something in there, you put it in there and then deal with whatever shows up. Okay. So what you do is the following. You start with R dot. This is very important. Minus AR. So far I have not changed absolutely anything. And now you are going to do a dirty trick. You insert at the output, for no apparent reason, some integrator. Sometimes people call this virtual dynamics. You need an integrator, stick it in there. Okay, there's a problem because this does not look like that one. I mean, the integrator is on the right, there it is on the left, but let's keep going. So now you have this variable called psi. It's an appended variable. It's a fake variable that we introduce. And now the equations of motion are r dot equal to minus AR plus BU, right? And what is this? If you have psi here, psi dot is equal to R. And you have a second order system. Second order system. So it's completely fake. I mean, you introduce there the integrated brute force. And now you write this in the usual form. X dot equal to minus A. So minus 8. So I'm calling R equal to X1, psi equal to X2, I hope. Yeah. So then you get X dot equal to minus AX plus BU. So minus A X. So minus A X1. And then plus B0U. And here the second component is psi dot equal to R, which is the first component. So you get 1, 0. That's your new system. So your system that consists of the original Nomoto model and some virtual dynamics or appended integrator, however you wish to call it, is described by this X dot equal to X plus BU, in which A is this guy and B is this guy over there. All right. So then what do you do? Then it's business as usual. Then you do the following. You concact this variable, which is K1 R1 Q1 R1 plus Q2 psi, which is in fact Q1 X1 plus Q2 X2, as you did before, except that you are penalizing something that looks a bit weird. So when you do the y square, you get X transpose QX, and now you have to minimize X transpose QX plus rho U square dt. All right. So now, under very general conditions, when you give MATLAB this system, and you wish to design an LQR control law, then naturally you get the solution. U equal to minus K1. Oh dear. X1 minus K2 X2. You see, the Kalman solution will give you this K1 and this K2. So this means that you have integral. This is R dot minus AR plus BU. And now you have this weird integral. This is R, this is psi. And you do feedback. So you get K1, boom, boom, and you have K2. K2. All right. The system will be stable. according to the principles derived by Kalman. So what do you do? Now you do sort of, here I have K2. You do a dirty trick. You grab this integrator and move it around to the left of this diagram. So from the point of view of stability, it's completely equivalent. So you get R E minus AR plus BU. You have R, and then you have here the K1. And now pay attention to what I'm going to do. I'm going to start here, and I'm going to copy this thing and put it on the left. So bloom, 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 bloom. K2 integral. And there you go. The integrator is now in the right place. And now you can add the reference. So that's how you insert integrators that you need in your design. You do brute force, you put them there, you view them as strange dynamics that now enlarge the dimension of the system. You do the design, you do the feedback, and then you shift everything to the left, and you get the beautiful system where you have proportional and integral action, and now the static state error is equal to 0. Okay. It's very important to understand this. Are there any questions? Oh, it doesn't matter. You can commute. Yeah, that is not the problem. You can commute. So anyone online would like to ask questions, please? Maybe not. Okay. You said, okay. All right. Thank you. So now let's go for a slightly more complicated case, but not terribly complicated. Suppose we go for Nomoto model number 2. So in the Nomoto model number 2, you still have the rudder, okay? But the output is the orientation. You want to steer that vessel, okay? So you get R dot equal to minus AR plus BU. So now you get R, and you do the integral. This is this integral has physical meaning because the angle of yaw is the integral of the rate of turn. Okay, what do you know? You see, you could think broadly in terms like this. All right, this is a first order system. This is a first order system, so I get a second order system. So I think that if I do an LQR design, I'll have feedback from this one, feedback from that one, and I get the second order system, and I can control the natural frequency and the damping and all that stuff. But suppose now that you have, because you were not careful installing the rudder, and there's an offset, so it's going to introduce a bias in you, right there. So boom, it's going to introduce a bias. What did I tell you? If you want to drive the steady state error to 0, when you look at the top layer, you have to see an integrator. There you go. So the steady state error is going to be equal to 0. But remember what I told you, very important. In order to learn the value that is required to cancel that offset of the rudder, you have to have an integrator on the left. Okay? So, you know, you do the same thing. You go for the appended dynamics, and you call this psi. So this is a very practical design now. So now what you have R dot equal to minus AR plus BU, psi dot equal to R, and psi dot equal to psi. You have a third order system. Well, three differential equations of order 1. So if you call the state R, psi, and psi, then obviously you have x dot equal to something times what? Oh man. X. So let's see. X1 dot is equal to minus AX1, and then it does not depend on any other variable. You get 0 plus the input times U. X2 dot is equal to X1, so you get 1, 0, 0. And X3 dot is equal to X2, 0, 1, 0. So this is A, and this is B. So when you do the LQR design using the tools that are available on MATLAB, you simply give it A, B, stuff like that. And now you go through the same procedure. You are going to invent a variable. Y is equal to a coefficient times R, a coefficient times psi, a coefficient times psi and C or whatever. I don't know. Okay. And then of course you can always write the square of these things as X transpose Q of X, where in this Q you have the K1, K2, and K3. So now you solve the problem. So you go on your computer and invoke the command. I think it's LQR. I don't recall. So you are trying now to minimize the integral between 0 and infinity X transpose. Oops. X transpose QX plus rho U square dt. Okay. And naturally, the solution will be in the form of a state feedback, which is minus K1 rate minus K2, rate minus K2 times the angle and minus K3 times that virtual variable that you have there. So you see now, when you have the Nomoto model number 2, you have R, psi, and you have psi. You have here the disturbance that we assume it's a constant, and now you multiply by K1, K2, K3. Yeah. K2. And here you have, well, there are many ways of writing this. K2 and K3. And then as a last step, what you do is to wrap up this integrator to the left. And so I'll try to do this here. Oops. You wrap it up to the left with a K3. So you don't need to have it here. And you put the reference. Sorry, this is all screwed up. This is K3. So now you get rid of this. And here you have a beautiful system where you have feedback from the rate, from the gyroscope, you have feedback from the angle itself, and you have integral action, you see? So now again, if you want to examine how this system behaves in practice, it's more complicated because now you have 3 states. When you have 2 states, it's okay because you look at the damping factor, psi, and so on and so forth. But when you have 3, it's more complicated. However, if you have these tools, what you can be certain of is that under very generic conditions, the solution will spit out K1, K2, and K3 that will stabilize the system. Suppose now that when you excite this with a certain desired angle, the thing oscillates a lot. So what you do is you try to penalize more the rate, the yaw rate. So you increase the K1 and hopefully the damping will come down. And when you do the body diagram, if somehow the bandwidth is very small, you decrease the rho. Now you have to be careful decreasing the rho because, okay, so always, and I did not place here the T wind up stuff. Always remember that when you have the Nomoto model number 2, and here you have the delta of the rudder, so I'm not considering the D, no matter what you do with feedback, you have to be careful because when you input a certain desired data reference, here at the input of the plant, you have actuators, which is the rudder actuator. And the rudder actuator typically is a 2nd order system with a certain bandwidth that you get from the vendor. Suppose you get 0.4 radians per second. So when you design this control system, it makes no sense to decrease the rho to get a very rapid system because it may very well be then, so this is the actuator, that would be pumping a lot of energy into this forbidden area, okay? Forbidden area. And that's it. That's a very simple introduction to LQR, but if you learn how to solve these problems, then you can develop your intuition and then you can get into more complicated problems, right? So now the big question is, well, you know, I covered nonlinear and now I'm basically going linear. I'll show you in the next set of slides because the nonlinear, when you want to do path following or stabilize to a point and stuff, I mean, you cannot use linear control laws. I mean, I don't believe that. But if what you are trying to do is to control a ship that, for example, moves forward with a certain nominal speed, for example, 5 knots, and you only do small deviations from the equilibrium, then you might as well do what we call linearization about this desired point. If you have other desired points, you do more linearizations, and then you design the controllers using LQ1. Okay, so all right. So any questions? I hope you are not totally lost. Chat.
LQR can only give linear control.
Sorry?
LQR can only give out linear optimal control.
Yeah. The standard theory is for linear systems. Linear, quadratic, regulator. That's what you can achieve. Okay? That's life. But it's a fantastic tool. So there's the question is, thank you, Stan. Okay. All right, now the next part I'm going to use some slides, so probably we should do some how do you say? Term break, some intermezzo here, and then we'll come back in about 10 minutes. Okay, we'll be back in about 10 minutes. Thank you. Okay. Yeah, because now I'll be going here. Now I have to share, right? Okay.
There is a Madras form. It's saying that it's saying that
No. Okay, you said? Okay, thank you. So you have a path, and suppose you are not concerned about the time. All that you want is for your car, your bicycle, or whatever, autonomously or automatically go onto that path and follow the route. So when you talk about path following, essentially time is not there implicitly, maybe, sorry, explicitly. Whereas if you are dealing with trajectory tracking control, it's completely different. In trajectory tracking control, you want to be at a certain position or successive positions at specified times. Okay. Why is it important to make this difference? Of course, I never worked on that, and I don't have any intentions of working on that. But it's obvious that if you have a missile trying to hit something, that missile has to track the trajectory and finally and eventually do the intersection. I mean, does that help very much? Oh, yes, I went along the path of that object up there and I'm happy. No, the military wouldn't like that. On the other hand, path following is very interesting because when you want to do a survey underwater, suppose you want to have one or more vehicles that go up and down, that take photographs and stuff like that. It doesn't matter very much if you are on a specific spot at a certain time. What is important is for you to go through this path to examine what is important along that path. So that's path following. It can be shown that when you design path following control systems, your maneuvers become, if properly designed, they become less jerky. So I tend to favor path following. So the big problem is if you have a vehicle, an autonomous surface vehicle or an autonomous underwater vehicle, or whatever, and you have a path, who gave you this path? The person that is hiring your services, and they say, I want you to do mapping of the habitats along this path. So how can I converge to that path and then move smoothly along that path? Now, don't get confused with the sentence there, tracking a desired speed profile. Now, you may wonder, well, you just told me that I don't have to track anything. This is different. For example, if I tell you that I divide this path in segments, and over this segment, I would like to go at 1 meter per second, and then 2 meters and 3 meters. It doesn't matter when you get there, but what is important is when you get there, then the speed should be the one specified. This is a very important concept. So it has nothing to do with tracking. So you track a desired speed profile along that path. Okay. Now, why are speed profiles important? In some circumstances, when you send these machines to sea, and you are trying to find out something, if you spend the whole time going up and down and up and down and up and down, then you lose a lot of energy and a lot of time. So maybe you should schedule your speed based on whatever you find out there. Oh, there is something very interesting. Now the speed should be very low. And okay, this is now barren land. There is not much there. Let me speed up. So please make sure you understand the big difference between trajectory tracking and path following. So in trajectory tracking, you are tracking a curve in 3D space, parameterized by time. So it's R3 cross R. In path following, you have R3, and it's parameterized by something else, as we shall see. So I wanted to show you this so that you get a glimpse. So this is the control architecture that we have for our vehicles, the Medusas. So what we do, suppose you have a desired path. how do you give to the system this path? There are many ways of specifying, and I'll show this to you. And for example, you should also state that you wish to go along that path with a certain speed, inertial speed that may be time varying. Okay. So based on where you are and based when the path is, so how do you know where you are? You go to the vehicle kinematics and you measure the position and possibly the orientation as well. So you bring them back to this path following controller. That then will send to what we call the autopilots or inner loops, the commands for desired linear and rotational angle or speeds. This is very, very, very common to see. When you want to design a path following control system for a vehicle, don't try to bring everything into the drawing board at the same time. Kinematics, dynamics, I mean, it's a big confusion. So what you do normally is to design the path following control laws based on the vehicle kinematics. Suppose, for example, that you have a ship at the surface and you want it to follow a certain path, you fix the speed, and then your control angle, and then your control is probably the heading angle. So what you can show is that if you have a strategy for the yaw angle, then the vehicle will approach that path and go along that path nicely. How can you be sure that inside the yaw is actually going to do whatever you wish it to do? So that's what we call the inner loop. So that's the outer loop, which has to do with kinematics, and the inner loop that has to do with dynamics. So at the kinematic level, things may be a bit more simplified. So you have the path following control law, desired path, the speed, you feedback some of the variables, and then you inject whatever variables. Now be careful, because this capital U should not be confused with small u. Capital U is the speed that could be path dependent. UD is, for example, if you command the yaw angle, you tell the vehicle, recruit your control system that you have on board, such that when I give you a yaw angle to track, you will be able to track it very well. You may also wish to track the speed. You may also wish to track the angular speed. Okay. So ultimately, when you put these together, you have the kinematics, you have the dynamics and the local controllers that sometimes we call autopilots. So this is borrowed from the air industry. And essentially you may be controlling using the speed, the yaw, and the yaw rate. So check that. The open loop, I should get rid of this. Okay, so sometimes the kinematic loop is called outer loop. It's the big thing. So implements a strategy that gives desired references for vehicle, reach this linear speed, reach this angle, reach this yaw rate, so on and so forth. And then the inner loops that we have to design have to accept these commands and have inner loops that make sure that these variables actually go and track very well whatever you ask them to do. Okay, so that's the general architecture of path following control system. Using this, sometimes people call this the inner outer loop decomposition, which is a very interesting word. Okay. When you start this, then don't get bogged down by all the dynamics and start by making this assumption. If my kinematic control law tells the vehicle that the heading should go to certain values, or the heading rate, or the speed, I'm going to assume that internally I have designed inner loop controllers that will respond very fast. ideally infinitely fast. Of course, it's not going to be infinitely fast, so there's a big issue here, because when you design a path following control law using kinematics, and everything seems to be working very well in simulations and in theory, then you ask the question, what happens if I introduce the inner loops? That's more complicated, but many people have looked into this. Okay. So what is the notation that one uses for? And the reason why I'm doing this, it's because when you go through all of these papers on path following, chances are that you'll find diagrams like this. So let's think very carefully. So you have an inertial reference frame. So this is all in the 2D plane, X, Y, and Y, I. And then you have the vehicle. The center is at Q, and this position is P. Okay. So the vehicle is out there doing something. There's this concept of where is it that I would like for the vehicle to be? And that's why I have another reference frame here that I call XP. And essentially I'm saying a long time, this virtual vehicle that is here is running, and without being too rigorous, I should make this one converge to that one. So this one acts as a reference. So there are these frames, inertial, body on top, and the body fixed frame with origin at Q. Oops. Okay. Now, when you are given a path, the problem is, how do you describe this path? And you use this expression, or you hear this expression, path parameterization, that at the beginning may be very, very confusing. And I'll explain to you why. So instead of writing, for example, if you have a straight line, that if you have x increasing linearly and y is equal to a function of x as a function of time, you don't do that because that's time is embedded there. So remember, this is where the vehicle is, and eventually you want it to converge to the path and do something nice and go along the path without any error if you have no disturbances. The vehicle itself, even though we are going to consider that the so-called side slip is very small, but in general, the velocity of the vehicle in inertial has two components, u and v. And then you have this desired position. That's where you'd like to be. And I may ask, how do I define where is it I would like to be? We have to think about this. I'd like to be under the sea. You know that song? Okay. All right. So that's it. Okay. I decided to show a few slides so that this would become crystal clear, because I know that some people at the beginning get a bit mixed up. So suppose the only thing you need to do is the following. You are out there on the lake and you wish to follow a path that is described by y equal to ax. Okay, so I'm not putting any time on this. It's a set of points that satisfy y equal to ax. And assume that the length, the total length of this line is L max. And I'm going to call this variable as you fly along, assuming you go along this path. At each point you have an L, which is the length traversed by the vehicle as I go along. As we'll see, it is very important in some cases to parameterize the path using the length or something else. So what is this? Okay, now if you compute L, then it's square root of x squared plus y squared. But because y is equal to x, then you get the length as a function of x. I mean, this is trivial. All this is trivial. So this means that now you have a way of parameterizing the path, I mean, the two coordinates x and y in terms of length. So x is equal to length traversed along as you move along, is equal to the length divided by square root of 1a plus a square. Y is equal to al square root 1 plus a square. This is what we call parameterizing the path using its length. So in other words, when you write the evolution of x and y, you use a single parameter that has to do with the length. And here you see a case where this is practically trivial. And now you do something else that will become very, very important for cooperative control. We are going to normalize the length and divide by the maximum. And this normalized length variable is called gamma. Gamma is going to be very important. So when you ask the system to do path following, essentially you are requesting that the vehicle come to this path and the gamma will increase up to 1 because you normalize by the Lmax. So it's a new normalized path parameterization. So now these computations are not, oops, I can't see here what's going on. Okay, so now how do you describe the points on the path? You say every point that consists of coordinates x and y is a function of gamma. And the gamma is between 0 and 1. And here is the parameterization x. So L is L max times gamma, L max times gamma. And therefore you have a parameterization in terms of this normalized length that sometimes we call the gamma. That's how you see most of the time. And I hope it will become clear later why is it that we need to do this? Why do you need to normalize this path parameter? Okay, you may get into something more complicated, well, probably not so much. Suppose you want a ship to go around a circumference. So you know that the length, the total length is equal to 2 pi times r. That's the L max. So in fact, when you go about this, the L is increasing from 0 to L max. It's obvious that if you want to describe x and y, you get r cosine theta, I r sine of theta. Now notice I am saying, let's parameterize using theta, which is the angle around, because it's more intuitive, and then we'll get back to the length. It's obvious that if you define this magical variable theta, a gamma, as theta divided by 2 pi, where theta is between 0 and 2 pi, then the gamma is between 0 and 1. And in fact, you have any point is a function of this gamma, cosine 2 pi gamma. So again, you have a parameterization of this circumference using a normalizing parameter. It's not exactly the length, okay? But of course, I can parameterize using length, because when you use the length, the maximum length when you go one turn is 2 pi r. So when you wrote x equal r as cosine r sine of theta, then and theta was, you are going to get something like this. Now you define gamma, which is 1 over 2 pi r. What are you doing here? You are dividing each coordinate along the circumference by the maximum through the maximum value. So again, gamma will be between 0 and 1, and you have a nice parameterization in terms of normalized length, which is the same as the other one, obviously, cosine 2 pi gamma r sine 2 gamma. Why is this so important? So I'll get into this later, but you see, I'll give you the intuition. If you have two ships and you want one to be running inside and the other one running outside, and you want them to be aligned radially, it's obviously that if you want them aligned radially, the inner one goes slower and the other one gets faster. But if you look at the gamma parameterization of both paths, because they are defined as 2 pi r, no, here, L 2 pi r, the gamma for one circumference varies between 0 and 1, and the gamma for the other guy will vary between 0 and 1. Now you can start talking, because cooperation is nothing but making sure that the vehicles maneuver so that the gammas are exactly the same. So when the gammas are exactly the same, you have to the inertial frame, and when you add the current specified in inertial coordinates, these are the kinematics of the vehicle. Okay, so this captures the external unknown disturbances. So equivalently, as I mentioned to you before, if you stack x on top of y and call it p, then this is a rotation matrix from B to I. This is surge and sway. This is the velocity of the current in inertial. Remember, this is in body. This is from body to inertial. This is in inertial. This is inertial. And then, of course, you have psi dot equal to R. Okay, so that's the vehicle kinematic model. Oops. So then you can start by considering simplified cases. For example, if you have an under-actuated vehicle, this means that you don't have a side thruster. So you cannot control directly the sway, the V. And I'm going to assume that the side slip angle is very small. And in this case, you have the kinematics very simple. The derivative of X, derivative of Y, and this goes through the rotation matrix. And then the derivative of psi is equal to R. And you can write in this form. It's a very, very simple kinematic model that you have here. Okay. Scenario 2. So didn't I talk about this one? No. Okay. So this is with external disturbances. I already mentioned this. And then you may have what we call fully actuated vehicles. That's when you have a vehicle and you have so many thrusters laterally that you can actually impart accelerations in all directions. In this case, you can actually control the U and the V at the same time. So it gets a bit more complicated. And you have the derivative of position is equal to the rotation matrix times, and so on and so forth. So what's the Medusa control system? When you have vehicles like this, you have to develop several types of controllers. One is called waypoint tracking. I don't like waypoint tracking very much. Waypoint tracking is when you give the vehicle a number of points, and you are supposed to home in on each one of these points. And when you get inside a certain neighborhood, you move on to the next one. Waypoint control. There's trajectory tracking that I'm not going to consider. That's when you want to track a curve that is parameterized by time. Okay, we are not going to do this. There's a path following. So in path following, you have the vehicle somewhere, and you have a desired point where you wish the vehicle to be. How is that defined? It differs from method to method, and we'll get into this. And point stabilization, it's a very interesting, sometimes we call these primitives, basic actions. It's when you want your vehicle to go to a specific point with a certain orientation, right? So this is the type of console that we use when we run our algorithms. And here you were seeing some images of cooperative path following and other types of formation control. So when you wish to build a vehicle like this, what things do you have to worry about? You have the, as I mentioned to you, you have the dynamics and the kinematics. So dynamics, here it is an underactuated vehicle, you see, because in you have the force of the propeller or propellers. In the V direction, lateral direction, you don't have any control, so it's not fully actuated. And upon rotating, you can apply a torque. So, so the kinematics is very easy. Derivative of position is the rotation times UV, psi dot equal to R. And then you have the dynamics. There you go. Okay. So please bear in mind that vehicle kinematics tries to accomplish certain things by controlling the speed, the angle, or the angle rate, and sometimes even the lateral speed when it is fully actuated. Okay. So there's a desired mission, and there's a controller that has to do that job. So you see, you have here the outer loop. That's what I mentioned to you. You see this structure in all of the vehicles that we build. So if you want to follow a certain path, you measure the position and conceivably also the yaw or yaw rate. You have the outer loop controller here that tells the vehicle at which forward speed or your angle or your rate it should go. And then you have to convert these specifications into torques and forces that are given to you by the inner loop controller. Okay. You see over and over this architecture, inner, outer, kinematic, dynamic, and even in when you deal with flying autonomous robots, you get exactly the same thing. All right. Your rate, so on and so forth. Now, when you have more than one vehicle talking to the other one, then we'll get into something called cooperation. It shouldn't be coordination, it should be cooperation, whereby one vehicle talks to the other vehicles in the neighborhood and trying to synchronize to achieve some form of formation. But I'm not going to get into that yet. Okay. All right. So I should warn you that when you open these papers on path following, don't be disturbed, because they start by talking about the famous Furness reframe. I don't know if you studied this or not, maybe at some point. Okay, so essentially what is this? If you have a path, okay, then the tangent to the path at one point is called the tangent. All right. So as you move with a certain speed that can be characterized by gamma, if you divide by the norm, then you get a unit vector. That's what you get right there. And then you have something interesting, which is the normal. That is directed to the local center of the curve. So if I go in a curve like this, the tangent is like this, and the normal is that way. For many, many years, people, okay, so why did people start using furnace array frames? Because when you are out there, this is not the best way of doing this. When you are out there and you want to converge to the path, you could think of a Serre furnace frame up here with the tangent and the normal. And if you look at the position of the vehicle expressed in this reference frame, you should make the error go to 0. And at the same time, if the vehicle has not side slip, to have the orientation parallel to the orientation of this reference frame. This was first introduced in control by Samsung long ago. It turns out that this has a major flaw because the normal is not defined when you switch curvature. So you have a big problem because, you know, you have the normal here, and then when you go through the inflection point, it goes to the other side. And now this is a disaster because if you want a vehicle that is on this side and is going slowly to that point and is reducing this point here, when you go through the inflection point, suddenly the normal goes to the other, and my God, all hell breaks loose. Suddenly it became negative. It was going so well and suddenly became negative. So, okay, this is an issue in 3D. In 3D, it's a real issue. So when you have aircraft and you want to introduce the furnace frame, you can't. It doesn't work. And there are many papers out there that are wrong, including one that I published when I was a baby. And I didn't know about this. And someone called my attention, oops, but not many people were aware of this. You could say, well, big deal. I mean, if the normal tends to flip, I don't let it flip. And in fact, in 2D, you can do that because if you follow the tangent, you just rotate to the right and you find the normal. Tangent, you rotate to the right and you form the normal, so on and so forth. Except that this will not work if you are in 3D. Because if you have a tangent, where is the normal? It could be anywhere on this perpendicular plane to the tangent. So you will get a very big problem. So some smart people from computer science came up with the idea that I'm not going to get into, that is called the parallel transport frame. What the parallel transport frame does in 3D is very much what I mentioned to you. Don't worry, I'll find a way of making sure that the normal and also the torsion does not flip. Otherwise, I would be in big trouble. So in what concerns us, don't worry, because the path frame could simply be tangent, normal at 90 degrees. So you avoid this flipping, okay? So you see here, the parallel transport frame is beautiful because you have T and N, and look at the Serre furnace frame, T and then T and bloop, it flips to the other side. And this is a killer because if you are trying to approach the path and you have a nice positive error that you are trying, and suddenly you get the negative error. And this will destroy your beautiful path falling algorithm. Okay. So now the plot thickens. And I'm doing this on purpose to try and show you the kind of notation that people use to write these papers. What is important is for you to learn how to read beyond the mathematical mumbo jumbo. Okay, so here is. What is the path falling problem in 2D? Derive a feedback control law for the vehicle's inputs. What are these inputs? Could be the speed and the heading angle, or could be the speed and the yaw rate. So that the error between P and PD goes down to 0. You see, I have not yet told you how we choose the PD. But it's a point. Sometimes we call it a rabbit that you want to follow. We call it a rabbit. I don't know. It kind of stuck. But I have to tell you how that rabbit is defined. Okay. So you have to bring the error to 0. And on top of this, you have to guarantee that if you specify a certain speed along the path, it's not given as a function of time. It's given as a function of the point where you are on the path. So you want the desired and the real you want to go to 0, or sometimes you don't work in inertial coordinates, and because we are parameterizing the paths by gamma, essentially you say the limit when t tends to infinity of gamma dot, which is the speed in the parameterization variable, is some desired value. And now pay attention to this expression. There's no big deal. You see, if you are going along the path, so it's PD of gamma. And you ask the question, what is the inertial speed or the inertial velocity? So you have gamma, you have PD, and then boom, boom, boom. Okay, so what you do is do the partial of PD with respect to gamma, because this has to do with the parameterization. You multiply by your desired inertial, this will give you a desired velocity for the gamma. Again, why am I making such a big mess? Because when you have more vehicles and they are all going about different trajectories, but if I normalize the gammas in the same manner between 0 and 1, then I should specify that I want the gammas equal, because then I reach cooperative motion control. And if they are equal, the velocity is exactly the same. Okay. Oops. So inertial speed, path parameter speed, and this is the path derivative, whatever. For example, suppose you have a path parameterized by length, all right? So gamma is equal to the normalized length. There's no quarrels about this, gamma. Using this path parameterization, you have x. So when gamma is 0, you are 0. When gamma is 0, y is 0. And then you pump up, and then it goes from this position to that one. And you are defining x and y as a function of gamma. As a function of gamma. So now check whatever I mentioned to you. Okay? Oh man. You see, this is the inertial speed. This is the gamma speed. It's obvious that the gamma speed, if you compute the derivative, is L speed divided by L max. It's obvious because you normalize by L max. But when you have more difficult situations, is this okay? So how do we compute this? It's the partial with respect to gamma, the partial of y with respect to gamma. You compute this and it comes L max, which you have there. So the formula is correct. In this case, it's trivial. You could do the same for this guy over here. So if you have L between 0 and L max, and you define x and y and define gamma as the normalized length, this is what you have. And now let's check again that this is true. You get here, you see, so you get the normalizing function, which is 2 pi r, because it has to do with the length of complete length of the circumference. So it's crucial when we get into path following and cooperative path following, that instead of working with L, we normalize the L using gamma so that they all speak the same language. And again, if I want the vehicle to go around an inner circumference and the other one outside, when should I declare victory? When the gammas are equal. So if I define the gammas by dividing the length by 2 pi r, the gammas are equal. and you reach cooperative motion control. Okay, so I don't know, maybe I overdid it. So now let's go for a unified overview. And I'm not going to bother you with all the methods. This is described in a paper that is in the process of being reviewed, where we do a summary of all path following methods, the most important ones that we know, together with practical experiments. So path following. So start by assuming that the vehicle does not have side slip. So in this case, U is something and V is 0. And you got the derivative is equal to the rotation matrix from B to Y and psi dot equal to R. Okay? Now you have a path that is parameterized by the arc length or some form of normalized arc path length. And at some point, you are going to have to declare where is it that you'd like for this vehicle to be. In other words, where should this, people call this the rabbit, because it sort of, you know, entices you to pray after it. Okay. All right. So here use a parallel transport frame. And in its most simple form, as was derived by Samson and Michaeli, the idea is the following. I'm going to try and find and have the distance between the real and desired. I have not yet said, how do you compute the desire? The length of this segment go down to 0. And then I would like to have this angle equal converge to the angle of the path frame, because, you know, if it doesn't have side slip 0, and then you go along, then this angle is exactly equal to that one. All right. So path following. What you wish to do? Find the speed and the heading, or the speed and the yaw rate, such that that error goes to 0. So you are sucked into the path. And remember now that I'm specifying the speed at which you wish to go in terms of the gamma variables. Why? Because no matter how many vehicles you have going around in circumferences, the velocity is obviously different, or the speed if you go on the outer circumference. But in terms of the gamma dots, they are exactly the same, because you normalize them, so they are always equal, and the speed is a constant. And then the other thing you wish to do is to have this error between your heading of the vehicle and the angle that the tangent makes with the path with respect to the north, tend to 0. Okay. So I tried to erase this, but I could not, because this is copied from a PDF. The rabbit may not be necessary. I'll talk about this. Okay. So how do you do this? You have the vehicle out there. You have the path. You define your path frame. So first, derive. Be careful when I say derive the dynamics of path following error. This is still kinematics. Okay. So derive the equations of motion that dictate the evolution of E. And then drive control laws that drive the path to 0 using nonlinear. Okay, so most path following control methods are done by controlling U and psi or rate of rotation. Sometimes it's a matter of taste. Path following has a long history, and there are more recent results. You see, it sort of started in 1993 with Michaeli and Samson in France. And then this student of mine, Lapierre et al., is the one that introduced the concept of the rabbit. Then my Vietnamese student Hung did some very nice work. Then you have some nice papers from the School of Norway at the NTNU in Trondheim, Torfossen and Breivik and Fossen. There's a beautiful path following algorithm that is very easy to implement, that was discovered by Pramod Maurya at NIO, and then you have other methods. Okay, so remember, when we were talking about control, the first thing that you have to do is, what is it that you wish to drive to zero? That's the basic question. So in this case, it's what? Two things. The distance between the vehicle and a certain point. I have not said yet how that point is computed. And the orientation between the vehicle and, or the error in the orientation between the vehicle and the angle that the tangent to the path makes with north. So two errors that you wish to drive to zero. Okay. So now I'm not going to get into the details because it would be utterly boring. So the first thing you do is, when you want to show that something goes to zero, you have to write down the differential equations that they satisfy. So you have to define the differential equation for EP. So you remember that's the derivative, which gives you the skew symmetric, PD, so on and so forth. And then, oops, what happened here? Okay. Oh, man. Okay. So you get a certain equation that looks a bit ugly for the evolution of the error and for the mismatch between the heading of your vehicle and the angle that the tangent on the path makes with the north. And notice that there's a very important factor here, which is called the curvature. So, you know, when you compute the parallel path frame and you have the tangent and the normal points to the local center of curvature. Okay. So you can actually compute the sine curvature of the paths at some specific point. And now, of course, I'm not going to show you where this thing comes from. This is the beauty of it. When you look at this and say, I have Q, I want to bring this error to zero. In fact, you don't have Y S1, you only have Y1. Because now here's the way this is computed. In the work of Michaeli and Samson, this point on the path, this is very important, is the closest point to the vehicle. So if it is the closest point to the vehicle, then you have this vector and you only have one component that we call Y, so you don't have S. Okay, there you go. And now you ask yourself the question, geez, how am I going to make these errors converge to zero? And that's where the beauty of Lyapunov comes into place. You see, this looks a bit complicated. So how am I going to actuate the search speed and the yaw rate, because Samson consider controlling with the yaw rate? And he comes up with this very interesting expression where it says, well, set u equal to d. I'm assuming here that the speed along this is supposed to be constant. But look at the r, which is the command. So the speed is fixed. This is the r. And the r looks very, very strange. There's a very fundamental point here, which is the following. If you are very far away and you want to drive this distance to zero, it's perfectly okay. But if at the same time you want to start by driving this error to zero, it does make sense because you may be very far away. This guy goes at 45 degrees. If this angle goes to the other one, it will go to 45 degrees. It will never get there. So Samson invented this approach function that sort of shapes the manner in which the vehicle approaches the path. In other words, you don't want to make the error equal to zero for heading, but you shape it according to a certain function such that when you are very far away, you go almost at right angles to the path. And then when the error starts being small, then you smooth out and go along the path. So the big mystery is, how did Claude Samson cook up this strange control law that you have here? You see, you have Y, which is the length of this thing. You have the delta, which is the shaping function. you have the curvature, so on and so forth. The way this is done is the following. You cook up a Lyapunov function, no matter how horrendous this may look. And because you have two errors, y1 and psi tilde, which is the difference between, you start with the difference between the vehicle and the angle of the tangent to the path, and then the difference with respect to the shaping function. So you square both of them. And that's a good candidate for Lyapunov functions. So if you go through all this ordeal that looks very strange, when you compute this, you get that the derivative is less than or equal to 0, use Barbalat's lemma, and you show that this converges exponentially. That's in the process. So here is the trick. When you don't know anything about the control law, I mean, this control law, as it is God-given. What you do is you write the Lyapunov function, you start computing the derivative, and now you ask the question, what should my input in R be such that LARSyS is less than or equal to 0? So you have to examine the derivative and have some inspiration and set the form of the control law. You can't get around that. I mean, it's a bit of work, but there's a crucial problem here. Look at I told you that in Samson, the point that you look at is the closest one on the path. But if you happen to go along a circumference and your vehicle goes directly through the center, there is no closest point. They are all. So this thing boils down. You cannot use this for more contrived situations. You have to use something else. But nevertheless, it's a beautiful method that was cooked up. And so instead of getting into the mathematics, so a little bit of history. So we knew this. Actually, Samson has a beautiful theorem where he proves conversion to the path. But here is the caveat. If you have a path that is smooth and suddenly you have a very small turn with a very small radius, you cannot possibly prove that your vehicle will converge to the path because chances are that you go through the center. So this means that he had to start the system very close to the path in order to avoid going through the center. And this is not acceptable. So it's interesting because for some time, we didn't know how to do this. We truly didn't know. Until I got a student, French student called Lionel Lapierre. Well, no, it was not him. It was a student. He was a student from Indonesia. And he said, Professor, I think the problem is if you restrict yourself to having this rabbit as the projection on the path, there's not much that you can do. Why don't you impart some other dynamics to this rabbit? That's why I called it a rabbit that moves back and forth and tries to help you converge towards the path. So it is no longer the closest point on the path, and now it has a life of its own and helps the vehicle converge to the path. And this works beautifully because now you have to control the speed and the gamma dot. Now the gamma dot is an extra control parameter, and then the R, and this works very well. And now I don't remember when, this was long ago. I went for a conference in Spain, and there was Morten Breivich that works with Professor Thoringe Fossen. And he said, I know how to solve the problem. And I said, I also know how to solve it. So what's your solution? No, I'm not going to tell you. Okay, so let's write on a piece of paper. Then we'll go to the presentation, and sure enough, he had exactly the same type of solution, which, I mean, it's no big deal, but it was very interesting. A bit of history. So again, the credit here should go to Didik Suetanto from Indonesia that vanished. I have no idea where he is. He vanished. I don't know. Okay. Okay. No problem. So in Michael and Samson, the point is the projection of the closest point. And as you know, that may lead you into troubles. But if you do this, well, I guess this slide is repeated, you concoct the Lyapunov function and you show that you converge to zero. There you go. I went back. Then you have the Lapierre. The Lapierre, fine. So now instead of controlling the U, the R, you also have to control the gamma. The gamma dot is like a rabbit with a life of its own. Like when you are very far away, it speeds up, hey, guy, come after me. Or when this guy very far away and ahead, hey, slow down. It's a beautiful solution. It works very well. Did you ever implement this one? Okay, so again, you go through the same stuff. I mean, you concoct the Lyapunov function based on the errand mismatch between blah 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 less than or equal to zero, and business as usual. Barbara lemma. Okay. So I'm going to spare you the ordeal of going through other methods, that some of them are beautiful. So I'll leave the slides with you, but I wanted to show you something. So we have developed the MATLAB toolbox for path following that you can use. And you can actually do simulations. You have the code in ROS, you have simulations in Gazebo. So you just go there to the archive or wherever you call it. Oh, I have something here. I think this is in simulation, right? Where you have this path that is called a Bernoulli path, and that's the way it is doing. Of course, it's in simulation, it works well. So now, what happens when we go in the water? Oops. Okay. So this is what it looks like. So we have a console, and you can have different parameterized paths or waypoints or whatever. And this is how you program your mission, just at a very high level. And then you transfer this to the vehicle, and the vehicle is supposed to recruit the controllers to do the job. So here are some simulations with different methods. I'm not going to bore you with this. It's very interesting to see the difference among them. And okay. And this is very interesting because here what you see, they are not synchronized, but oops. Wait a moment. So what you see is the, oh. So you have the MATLAB simulation, you have the real stuff, you have the Gazebo visualizer, and you have whatever you see on the console. It's a bit hard to see. So here it's going through the Bernoulli. So it's a pleasure to be able to implement these things and go from theory to practice using ROS and Gazebo. And then you have these beautiful things operating. And then, of course, you have similar things for cooperative motion control. All right, so now, so there are some references that I will leave there. Now, the interesting thing is, if you ask me, so, but who came up with some of these methods? Well, we have already done some very interesting work. Well, I shouldn't say interesting. Who am I to say it's interesting? Cooperative control of autonomous air vehicles with people at the University of Illinois, mostly Illinois, Naval Postgraduate School, so on and so forth, on cooperative control of autonomous air vehicles. And there you need exactly the same algorithms, except that now you are in full 3D, which is fascinating. So let me throw you a challenge. I mean, this would be beautiful if we could do something like this. There's a team at my school is technical, called the Solar Boat Team, 25 students, mechanic, electrical, solar power, and blah, 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 so on and so forth. And the idea is, how do you make this thing work? Now, I was not involved in the design of the mechanics, and I was only involved in the controls. So the credit goes to most of the students here. But I tell you, it's marvelous to see these things in operation. So essentially, you take off, the drag is drastically reduced, and then you have to control the pitch, you have to control the yaw, and it's a beauty. I think this is a different one. Yeah. So at this point, this boat is not fully autonomous because you have a pilot on board that controls the speed. But the roll and the pitch and the altitude, the height above the sea, above the water, they are controlled automatically. So as you can imagine, this is a fascinating problem. So there you go here. I mean, you can learn so much by building one of these things and making it work completely autonomous, doing path following, controlling the thrust. I mean, there's no end to this. So what is the status? I shouldn't say we, the team developed this vehicle. Like I said, I only cooperated on the controls part. But to me, it's a fantasy. I mean, if for example, it would be lovely to have one of these hydrofoils, and if you want to inspect something underwater relatively far away from land, you could boom, send one of these with little drag, and then it comes down and then drop a remotely operated vehicle to do the inspections and come back home. So this would be a fantastic project. So if you ask me what's happening around the world, okay, so this is the way you do the design. You see, you have enough stuff to keep you busy. The vertical plane controller, the dynamics, the cinematic. And if you look at the control system, everything is there. So you have the reference, integral action, anti-wind up, except that now you have 4 more variables because they have to do with the heave and pitch rate, but it's LQR design. This you do using LQR design. There's a company in Sweden. It's an interesting story because you met Navin, right? No? Where is Navin from? Maharashtra? No, Karnataka. Navin Krasta. Where is he from? Karnataka. I think so. Anyway, he was a postdoc, so he got his PhD at IIT. I think it was Mumbai. I don't remember. And he thought of himself as a big, important mathematician. And I told you, Navin, in order to be recognized as a mathematician, you have to be super good. I'm not saying you are not, but. And then he got this fantastic job in Sweden, it's a company called Candela. And each one of these babies costs $300,000. It's not even fully autonomous. So gosh, you can make this autonomous. So in other words, the pilot, as the solar boat that I showed to you, controls the speed and I don't know what else, but there's so much to do over here. And you guys have fantastic facilities here. Of course, it would have to be some form of teamwork, but I think it would be very cool, very interesting. Okay, so I'll stop here now because I don't know why my head is a bit more. Maybe it's the heat. Okay, so gentlemen on the other side of the world, tomorrow at 3 o'clock for the final run, okay? And then we have to send this warning to everyone. So please don't think that this stuff about path following and it's extremely complex. No, once you get into it, you'll get used to it. And these things are used in practice, which is very, very, very important. Okay, any questions? You send my faithful attendee, how do you say? Okay, you have any questions? Avanish, questions? Okay. Okay, so I'll see you tomorrow at 3. Thank you very much for having come here. And then And then we'll place all the slides here and everything if you want references and stuff. Check the page of Candela. Maybe you'll get some ideas for a project. I think it would be wonderful. Okay. Okay. Thank you. Thank you. Yeah.